Time for us to do some problems involving partial fractions. A lovely stroll down algebra lane. Because the idea of partial fractions is not a calculus one, it's an algebra one. It's an algebra technique that lets us take rational functions, polynomial over polynomial, and pull it apart into nice, easier to digest pieces. And while it's a lovely idea, it is one that takes a little bit of practice. So we want to make sure we take our time. And yes, it's really important to do practice. So if you're following along with the video, make use of the pause button. See a problem? Try it out yourself first. Can you break it into the right form? Okay, can you see how to solve for the coefficients? And with practice, you'll see it's actually not so bad. But it does take practice, so make sure you're putting in the time. And as you do it, you're going to become amazing. All right, let's begin. Our first problem. Find in simplest form the value of this integral. And it's a definite integral, 6 to 8, 8 over t squared minus 8t plus 15 dt. And you might say, what does simplest form mean? It tells us our answer should consist of a single logarithm. Okay, well, I don't know. Let's see. Well, where to begin? Now, when we look at this, we say, okay, it is definitely a rational function. Polynomial over polynomial. So the process is, we ask ourselves, do we need to do long division? The answer is no. And the reason is downstairs, it's a second degree. Upstairs, a constant, or we can think of it as a 0th degree. So already the higher power is downstairs. No long division. Woohoo! Check. Okay, so what we're going to do is we're going to say, okay, look, the integral from 6 to 8 of 8 over t squared minus 8t plus 15 dt is something. Well, now we're going to do a lot of work on the side, then come back to the integral at the very end and work it out. What's a lot of work on the side? Well, our side work is to say, how do we rewrite this expression? So we begin by saying, okay, let's look at our denominator. We need to factor it. It factors, and what does it factor as? Well, I need two numbers that multiply together to give 15 and add together to give 8. Well, that's not too hard to imagine because 15 is 3 times 5. So we're going to have t minus 3 and t minus 5. Okay, so now that we know what our terms are in our denominator, the idea of partial fractions says, look, this can be pulled apart as we have something over our first term, t minus 3, and something over our second term, t minus 5. All right, so that's the right form. And what do? Well, the form is based off of our denominator. So we see, okay, there's a t minus 3 to the 1, so there's going to be a t minus 3 term, t minus 5 to 1, there'll be a t minus 5 term. Okay, so that's our right form. The only thing left to do for partial fractions is, what is a and b? So the way we can do that is to say, all right, clear your denominators. And the way we'd clear our denominators is to multiply everything by enough to get rid of that denominator on our original side. So multiply everything by t minus 3 times t minus 5. All right, well, so we're going to end up with 8 is equal to, well, a times, here the t minus 3's cancel, so we're going to have a t minus 5. So a times t minus 5. And then here the t minus 5's cancel, so we're going to have a b times t minus 3. Okay, good. So we have to figure out a and b from this. So we're going to do it by two different methods just to sort of illustrate. We're not always going to use two methods, but we'll do it once or twice just so we can get a flavor for what's going on. All right, so what are our two methods? Well, the first method I like to call choose wisely. All right, Well, what does that mean? Well, what you have is you say, look, it's a polynomial and a polynomial. So it has to be true for all choices of t. And so when we say choose wisely, we're going to pick some nice values for t. So here we want to say, look, pick a value of t which makes it easier to figure things out. And so that's why we say choose wisely. Well, what makes things easy? Well, if we can start getting zeros in there. So looking here, what are some good choices? Things that make zeros. Well, how about t equals 5? If we plug in t equals 5, then that tells us what? 8 would equal a times 0, which is 0, plus b times 5 minus 3. 5 minus 3 is 2. So 8 equals 2b. Okay, that tells us b has to be 4. Is there another good choice for t? Something that would, again, simplify things. Aha! T equals 3. Okay, well, so let's do that. T equals 3. What happens? We get 8 equals, all right, 3 minus 5, well, that's negative 2. So minus 2a. But now, no b, 0b. So that term, gone. Great, beautiful. So we come to the conclusion that a is negative 4. Okay, we've now solved for a and b. And so what you can do is you can say, oh, okay, so this is really minus 4, and this part is really positive 4. All right, good. Now, we actually can stop partial fractions and go back to our problem. But I want us to do the other method, right? Because I said there were two methods, just so you know what they both are. And they're both useful. And sometimes it works best when you combine the ideas. So, what's option 2? Option 2, when we're trying to solve, says, look at the coefficients. Now, what does that mean? Well, what we can do is we can say we have 8 equals, and now you imagine expanding and grouping. So let's look at our coefficients of powers of t. Well, we're going to have at plus bt, so we're going to get a plus b times t. And then here, about the constant terms, there's a minus 5a and a minus 3b. So we're going to have plus minus 5a minus 3b. Now, what nice fact about polynomials is two polynomials are equal if and only if all of the coefficients are equal. So when I look here, I say, okay, that tells me that this minus 5a minus 3b, that constant term that I'm seeing here has to match up with the constant term I see there. And you say, okay, well, what about this? What is that matching up with? Well, it's matching up with a 0t, because there's no 0 over there. So, all right. So we come to the conclusion that we have really two nice facts about a and b. So we get that a and b has to equal 0, so the coefficient of t. And on the other hand, we get that minus 5a minus 3b has to equal 8, our constant. Now we have two equations and two unknowns, and we're like, okay, now we can solve. So we can do all sorts of things. So for instance, say we multiplied our first equation by 3. 3a times minus 3a plus negative 5a would be minus 2a. The 3b minus 3b would be 0, and the 0 plus 8 would be 8. So we would come to the conclusion a is negative 4. Well, once you know a is negative 4, b is negative a, so we can say, all right, b is negative 4, which is b equals 4. You'll notice we get the same answers. Well, of course we're going to get the same answers, because regardless of what process we do to find the coefficients, we're going to have to, at the end of the process, be the same. So our two basic ideas: look for good values of t. Choose wisely. Try to get zeros. Look at coefficients and compare coefficients. And remember, you have to do expanding and grouping all the coefficients together. And between two of them, and you can use them together, between the two ideas here, we can do anything. All right, so we've now done our partial fractions. We go back to our regularly scheduled calculus problem. So we have, this is the integral from 6 up to 8, and we have minus 4 divided by t minus 3 plus 4 over t minus 5 dt. Well, great, wonderful. We're ready to go, because what happens here? Each piece is easy to work with. In particular, if I have 1 over t minus something or t plus something, it's a log. So this is minus 4 log of t minus 3 and plus 4 log t minus 5. And evaluate from 6 to 8. And now we can see, oh, that's why our answer should consist of a single logarithm, because we have everything involved has logarithms. Well, what does this become? When we plug in 8, well, okay, we're going to get minus 4 log 8 minus 3, 5, and then plus 4 log 8 minus 5, that's 3. And then we're going to subtract, plug in 6, minus 4, and here log of 6 minus 3, so log of 3 plus 4 log of 6 minus 5, 1. All right. Well, the good news is one term is very easy to handle. That is the log 1. Okay. Phew, gone. All right. Wonderful. And we also see something nice here. Minus minus makes a plus. And so we say, okay, minus 4 natural log 5, and then plus 8 natural log of 3. Now it says we want to reduce to a single logarithm. So what can we do? Well, now we can use properties of logs. So for instance, the fact that we have a constant in front says, hey, 8 log 3, I can think of this as log of 3 to the 8th power, minus 4 log 5, well, I can think of as log of 5 to the 4th power. And finally, when I see a subtraction of logs becomes divisions. So we get log of 3 to the 8th power divided by 5 to the 4th power. And we're done, right? That's as simple as we can get. Now you might say, wait a second, don't we need to multiply out? 5 to the 4th is 625. 3 to the 8th is something. I don't know what 3 to the 8th is. It's going to be a big number, though. And no, this is fine. Perfectly fine. Great. Wonderful. What a beautiful problem. Nice answer, too, right? Down to just a single term. Okay, but now you have the idea, right? We're going to take our original integral, apply partial fractions, pull it apart into simple pieces, and work each piece. So it's not so bad. So let's keep going. And the more we do, the better we get. So our next one, another definite integral. Find the integral 1 to 2 of 2y cubed minus 5y squared minus 2y plus 3 over y squared minus 3y. Now, first thing we always check, well, first off, is it a partial fractions problem? And yes, it's a rational function of a rational function. So partial fractions, great idea. The next thing we say, do we need to do some long division here? And the answer is yes, because what do you see? Well, if you look, the power on the top is larger than the power on the bottom. So that says we need some long division. So the first thing we need to do is divide. All right, so we're going to take our term y squared minus 3y and divide that into 2y cubed minus 5y squared minus 2y plus 3. Now, the way we do long division is we always ask ourselves the question, what's happening with our leading terms? Okay, so I have y squared. What do we need to multiply y squared by to get to 2y cubed? That's our question. All right, that's actually not so bad, right? Well, we say, okay, well, we need a y and we need a 2. So we'll need a 2y. So now take 2y times the whole thing. So a 2y cubed, which is exactly what we need, and then a minus 6y squared. You see, if I took y squared minus 3y and I got 2y out, I had to have a 2y cubed minus 6y squared involved. So another way to think of it is I've now accounted for this part right here. And what I need to figure out is, well, what's left to account for? So I'm going to take out what I've already accounted for, subtract it out. Minus 5y cubed minus, that's 5y squared, minus 6y squared, the 2y cubes cancel, is y squared. And then there's a minus 2y and a plus 3. All right, we repeat the process. Okay, we look at the leading terms. I have a y squared. I have a y squared. What do I need to multiply y squared by to get to y squared? Well, 1. Okay, that's not so bad. So I'll put a plus 1. Again, multiply y squared minus 3y, subtract. The y squareds cancel. Minus 2y minus 3y makes y, and then there's a plus 3. All right, great, beautiful. Now, we can say, okay, y squared, y, stop, the game's over. As soon as the power here drops below the power there, we don't do any more division. We can't. This part right here, this is our remainder. Okay, so what does that tell us? It tells us the following, that our integral problem is actually the integral from 1 to 2 of 2y plus 1, what we got here, plus our remainder, y plus 3, over our divisor, y squared minus 3y. Now, the first pieces are easy to do, and polynomial life is good. The last part, the y plus 3 over y squared minus 3y, well, for that, we need to go do partial fractions. Okay, so what do? We get the following. We'll have y plus 3 over y squared minus 3y. So we factor it. It's actually easy to factor. They both have a factor of y. So this is y times y minus 3. Now, the denominator tells us the right form. And we see, all right, we're going to have a y term and a y minus 3 term. So when this pulls apart, it'll be something over y, and it'll be something over y minus 3. So we put in our somethings. We just have to figure out what a and b are. Clear your denominator. Okay, so multiply everything times y minus 3. And when we do that, we're going to on the left-hand side, y plus 3 equals, the y's cancel in the first term, so a times y minus 3, and the y minus 3 is canceled in the second term, b times y. So, let's choose. But remember, choose wisely. For as a good choice brings us closer to the answer, a bad choice takes us further from it. What's a good choice? I think 0 is a great choice, right? Because I see if I plug 0, that's going to knock the last term out. So, choose y equals 0. All right, great. Well, what does that tell us? Well, it tells us that 3 is equal to minus 3 times a. And then that term drops out. All right, well, that tells us a is minus 1. Okay, how about the other one? Well, if you want to make that term 0, pick 3. So, pick y is 3. All right, 3 plus 3 is 6. And then we get 0 times a equals 3 times b, 3b. Coming to us an exciting 3b action. Well, that tells us b needs to be 2. All right, lovely. All right, so what do we have? Well, what we have now is we know how to break things apart. So we're going to choose a is really negative 1, and b here is really 2. So let's update our integral again. So we still have the integral 1 to 2 of 2y plus 1. Then we're going to have a minus 1 over y. Then we're going to have a plus 2 over y minus 3. All right. So you'll notice at this point, we still have yet to do any calculus. What we've been doing is pulling our original expression, and now we're like, wow, we've pulled it apart so well that all the pieces that are left are nice, easy to digest things as far as the calculus is concerned. Because that's where we want to be. We want to be at the point where the calculus part is not so bad. Well, so let's finish it. All right, so what do we have? Well, the individual pieces, we integrate, we get y squared plus y minus log of y, all right, plus 2 log of y minus 3. All right. Now, you might notice, technically speaking, I'm just going to point out, whenever I take integrals of log, it's logs of the absolute value, and it doesn't really matter, just pay attention. And I'm doing it here because I'm kind of seeing where we're evaluating, and we want to make sure that wherever we plug into a log is positive. And so if you say, oh wait, whatever I plug in, if it's potentially negative, I throw absolute values. Okay, that's just the integral. Just nothing secret. I'm not cheating here. I don't want you to think, oh, Steve is cheating. No. I wouldn't do that. Not to you. We're friends. All right, and then we're going to evaluate 1 to 2. Okay, so plug in 2. 2 squared, 4 plus 2. All right, that's 6 minus log of 2. All right, plus 2 log of 1. Subtract, plug in 1. 1 squared plus 1. 2 minus log of 1. And then plus 2 log of 1 minus 3 is negative 2, but we're taking absolute values. So that's a log of 2. And now, well, we're pretty much done. We see the log of 1s drop out because they're 0. 6 minus 2 is 4. Then we have a minus log 2 minus 2 log 2. So that would be minus 3 log 2. And of course, if we wanted to, we could say, 3 log 2, you could put the 3 up in the exponent. So I could also write this as 4 minus log 8. And that's a pretty nice answer. Pretty clean and not so bad. Good. Lovely. Wonderful problem. Wonderful problem. All right. Well, let's keep going. All right, our next problem. Find the integral of t squared plus 1 over t minus 1 times t minus 2 times t minus 3. All right, good. Partial fractions, we can just see it. It's a polynomial over polynomial. Life is good. Now, first thing, do we need to worry about long division? Well, let's not just hastily say yes or no. We say, look, there's a t squared upstairs, which means it's degree 2 upstairs. Now downstairs, because it's multiplied here, we just sort of say, okay, there's a t, a t, a t. So if you were to expand out, it'd be a t cubed. So the higher power is already downstairs. Okay, no long division. Good. So, all right, what happens? Well, this is all about partial fractions and getting the form. So we say, okay, it's already been factored for us. That means somebody really likes us. And we like them because they gave us such a nice problem. So we're going to have t squared plus 1 over t minus 1 times t minus 2 times t minus 3. Now, partial fraction says we're going to break this up. And on the other side, we look at the denominator. The denominator determines the form. So it says, all right, we have a t minus 1 term. Then there's a t minus 2 term. And there's a t minus 3 term. All right, so it's going to be A, B, C, where those are to be determined. All right, good. Now we have the form. In some sense, it's almost one of the hardest things about partial fractions is getting the form. But once you get the hang of it, the form actually seems fairly natural. So we proceed. The next thing is clear our denominators. So we're going to come here and we're going to multiply everything by the denominator. We multiply by this denominator here, t minus 1, t minus 2, t minus 3. And once we do that, we're going to get to the following. T squared plus 1 is equal to A. And now we say, look, the t minus 1's cancel. So that'll be times t minus 2, t minus 3, plus B. The t minus 2's cancel. So t minus 1, t minus 3. Here, the t minus 3's cancel. And so we're going to be left with C, t minus 1, t minus 2. And at this point, you're probably like, we're going to be here for a while. Or maybe we can choose. But choose wisely. Choose wisely. So what are some good choices? And remember, the theme is choose things that make things zero. Not surprisingly, you're like, well, choose things that would be bad if you chose them here. Those are what are making things zero. And so we say, okay, well, I see, because I see some t minus 1's, let's try t equals 1. 1 squared plus 1 is 2. Equals. All right, we're going to have A times 1 minus 2. That's minus 1. 1 minus 3 is a minus 2. So that'll be actually a 2. So 2 equals 2A. Then we'll have 0B and 0C. Beautiful. So A is 1. Well, that's quick. How about t equals 2? Okay, right, because there's a t minus 2. 2 squared plus 1, 5. Okay, because of the t minus 2, when plugging 2, gone. And the last term is gone. Middle term, we're going to have 2 minus 1, which is 1. 2 minus 3, which is negative 1. So we're going to end up with negative b. Okay, so that says b is negative 5. Well, that's nice. Okay, one more choice, and we're good to go. Well, t equals 3, right? 3 squared plus 1. 9 plus 1 makes 10. T minus 3, when you plug in 3, that knocks out the first term and the second term. 3 minus 1, 2. 3 minus 2 is 1. So we're going to have 2c. So 10 is equal to 2c. Okay, so c is positive 5. Great. Wonderful. So that tells us we know our right choices for A, B, C. So we say, okay, A is 1, and B is negative 5, and C is positive 5. So we're done with the partial fractions. We go back to our regularly scheduled integration problem, and we say, hey, this is equal to the following. It's the integral of 1 over t minus 1 then negative 5 over t minus 2, so minus 5 over t minus 2, and then positive 5 over t minus 3. And now we say, well, look, each one of those is nice. They're very clean pieces. So we have log of t minus 1, that's the first integral, minus 5 log t minus 2, that's the second, plus 5 log t minus 3, that's the third, plus c. And we're done. Alrighty. See? Look, we got it. It's not so bad. Once you start getting the hang of it, it just says, okay, put in the right form, clear your denominators, make some good choices, find your constants, and then, boom, into the integral, and away you go. Life is good. Life is good. All right. Well, great. Good. Let's continue. So, our next problem. Here we go. Find the integral of 3 natural log of x plus 3 divided by x squared dx. Now, is this a partial fractions problem? No, it's not, right? You're probably saying, whoa, wait, hold on. I thought we were doing partial fractions today. The reason it's not a partial fractions problem is it's not a polynomial on the top. It has a log of x plus 3. So, okay, so it's not partial fractions. It appears somebody seems to have slipped in something that's different. And in particular, this feels more like an integration by parts problem, doesn't it? Because you have that log of x plus 3. It's like, I don't know if I really want to integrate a log of x plus 3. I agree. Indeed, I would probably not want to do that. So let's not worry about partial fractions right now and say, okay, if we saw this integral out in the wild, what would we do? Well, we'd probably say, look, I can think of this as two pieces. And there's one piece, log of x plus 3, which looks a little bit, not something I'd be excited about integrating. But the other piece is actually not so bad in the grand scheme of things, the 3 over x squared dx. So the nice thing is integration by parts says, hey, you can make progress if you can integrate just a part of it. And the other part, you can differentiate it. So we say, all right, we'll do that. So this log of x plus 3, we'll make that something we differentiate, 3 over x squared dx. Well, that we can integrate. So we have, okay, the derivative of natural log of x plus 3, 1 over x plus 3 dx. If you integrate 3 over x squared, you can think of it as 3x to the minus 2. What would that be? Well, okay, that's, you add 1 to the power, so it'd be 3x to the minus 1, but then you would divide by that minus 1. So what you'd end up with is that v is minus 3 over x. All right, so, okay, so that's the integration by parts. And it says what? Well, we have this is equal to uv minus 3 over x, natural log x plus 3, and then minus the integral of v du. Okay, so what is that? Well, notice there's already a minus, so minus to minus becomes a plus. So I'm using the fact that there's a minus there. Then we have 3 over x times 1 over x plus 3. I can write that as 3 over x times x plus 3 dx. All right, so we did integration by parts, and now we say, all right, we have to deal with that integral. But notice what kind of integral it is. It's a polynomial over polynomial. In other words, it's a rational function. We have the technology. We have the tools. And let's just pause here and just sort of like celebrate how interesting this is. Because notice, what did we start with? Well, we started with something that says, well, that doesn't look pleasant, and let's do an integration by parts because really that seems to be the only way we can make progress. So we did an integration by parts problem, and after we did it, we got, we've changed now so that now instead of having to do an integration by parts problem, now we're having to do a partial fractions problem. There's this sort of idea that says, look, deal with the problem you have right now. And so we said, all right, the problem we have right now, that requires a certain tool. And we applied our tool, made one step closer in our terms of our understanding. All right? And now we say, great, now you have a new problem. Begin with that problem. So we say, okay, great, reset and say, look, I really don't care I came from there. This is my problem now. Let me figure out what to do with that. And so it's kind of a nice idea that says, just to say, don't worry about getting all the way to the end right away. Just say, what can I do with my problem now? Do something. Say, okay, now let me reset. What do I need to do next? And so we wouldn't want to keep doing integration by parts here because that won't make progress. We really do want to do more partial fractions. All right. So here we see, all right, don't need to do long division because we can see upstairs it's the constant, downstairs it's a quadratic, there's an x squared. So we'll do some work. We'll do it over here. Okay, so we have 3 over x times x plus 3. The denominator determines the right form for partial fractions. There's going to be something over x and something over x plus 3. Okay, so the a and b. Now, clear the denominators. So we're going to multiply both sides. X times x plus 3. So we have 3 equals, the x's cancel, so that's a times x plus 3. Here the x plus 3's cancel, so it's b times x. And now we must choose. And we choose wisely. Well, there's two really obvious candidates. If we choose x equals 0, all right, that knocks out the second term, and we'll get 3 is equal to 3a. So a equals 1. If we choose x equal negative 3, okay, we'll get 3. And here, the a term drops out, equals minus 3b. Okay, so that says what? B is minus 1. All right, well, great. Beautiful numbers, right? 1 and minus 1. So, returning to our problem now, we say, look, we know a and b. So, look, a here is 1, and b is minus 1. And so, our integral problem continues. We still have in front our minus 3 over x log of x plus 3, and then plus our integral 1 over x, see our a over x, minus 1 over x plus 3 dx. And now, well, we're in our home stretch. So minus 3 over x natural log x plus 3 plus integral of 1 over x natural log x, and then minus integral of 1 over x plus 3 minus natural log x plus 3, and plus c. Done. Done. It's great. It's kind of fun when we start to see, oh, these ideas that we're talking about, they're not completely independent. It's not like, okay, there's this one technique and over here, and there's this other technique over here, and there the twain shall meet. That's not how calculus works. All our ideas can blend together, and we can see that in some problems we can have combinations of ideas. And in some integrals, you can pull out like half a dozen different techniques to get to our answer. So don't think of these as little individual compartments that it's like, okay, if I'm using this tool, I can't use any other tool. That's not how calculus works. It's not how solving problems work. Use all the tools, and you have to make sure you're comfortable with all the tools. All right, that's I like that problem. It's a really good, fun problem. Okay, good. Now, I think this is going to be an interesting one because there's a lot going on here. So let's look at it. Find the integral 4 minus 2y over y squared plus 1, y minus 1 squared. All right, now, it's interesting for two things. First off, if you look in our denominator, you see there's a y minus 1 squared, which means we have a repeated term. We haven't had that yet. You'll also see there's a y squared plus 1. Now, what's this? Well, this is, if we talk about the language of partial fractions, the very fancy way of saying this is an irreducible quadratic. And that's just a really long way of saying it doesn't factor as, t minus something times t minus something. It says that's as simple as you can get it. Unless, of course, you wanted to get into complex numbers. But that sounds complex, so we avoid that discussion. Now, what's happening here? Well, this would be a repeated linear factor. And both of these cases are places where people can get a little bit like, wait, what? Hold on, what's happening here? So we do want to be careful. And this one, we want to take our time and make sure we get the right form. And so let's be patient here and talk about what's happening. So we do our partial fractions. We say, first off, check your degrees. Upstairs, it's degree 1. Downstairs, it's going to be a degree to the 4th because you have a y squared and another y squared. So we definitely are okay without doing long division. All right, so the hard part about this problem is the following step. And so we're going to try to do it carefully. And that is, what's the right form for the partial fractions? And for that, what we do is we say, all right, what we should do here is we look at the denominator. The denominator always tells you the form. So you have the first term, a y squared plus 1. So that says you're going to have something over y squared plus 1. And that takes care of the y squared plus 1. Check. The y minus 1 squared, well, what you have, since it's y minus 1 squared, is you have to build yourself up. So you're going to have just a single y minus 1, and then you're going to have a y minus 1 squared. So those will be your pieces here. Now to the numerators. Because it's irreducible quadratic, you're not going to have just a constant. You're going to have ay plus b. Here, linear term, so you're going to have a c. And here, it's still a linear term. But even though it's a linear term to a higher power, it's still linear, so it's going to be, again, a constant. All right, so that's the right form. Now, there's a nice check to see, do I have the right form? Which is the following. Ask yourself, how many unknowns do I have? See, I have 4. I have A, B, C, D. That's 4 things I don't know. Now, the number of things you don't know has to match the degree of your denominator. So y minus 1 squared comes from those two. Well, if you look, it's a y squared times another y squared, which is y to the 4th. So there's 4th degree polynomial. There's 4 unknowns. That's not a coincidence. So the number of knowns will always match the degree downstairs. So when in doubt, just check to see, hey, do these things line up or not? All right, so in our case, they do. Good, good. Now, the process continues as before. Clear your denominators. So we're going to multiply everything by our y squared plus 1 times y minus 1 squared. So we're going to get 4 minus 2y equals, well, ay plus b times, here, the y squared plus 1 cancel, so y minus 1 squared plus, all right, c. Now, 1y minus 1 cancels, so we'll get y squared plus 1 times y minus 1. And here, the y minus 1 squareds cancel, so we're going to get d times y minus 1 squared. Oh, sorry. Those are what canceled. D times y squared plus 1. Sorry. Good. Whew. All right. Well, now the question becomes, do we have some good choices? And, well, do we? I think we have at least one good choice. And that is 1. 1 is a great choice. So let's choose y equals 1. If we choose y equals 1, what do we have? Well, we'll get 4 minus 2, which is 2. The first term will go away because of the y minus 1 squared. The second term will go away because of the y minus 1. The last term, it'll be d times 2. So 2 equals 2 times d, or d equals 1. Ha! Progress. Progress. Great. Well, unfortunately, that's about as much progress as we can pick. Any other thing we choose, we're not going to get enough cancellation. So, what now? Well, now we're going to, as they say, bite the bullet, and let's expand out and see what we have. Okay, so we'll work on our terms here. So, expanding, well, okay, so we're going to have a times y plus b times y squared minus 2y plus 1. And here we're going to have plus c. And then if you multiply that out, well, okay, so y squared times y is y cubed minus y squared plus y minus 1 plus, well, we know what d is. D is 1. So plus y squared plus 1. Okay, so let's continue multiplying. So ay times y squared, that's ay cubed. Ay times minus 2y, minus 2ay squared. Ay times 1 is ay. And we have b times y squared. And then b times minus 2y. And then b times 1. So that's plus b. And then we have the next terms. Okay, we're running out of space, so we'll go to the next line. Cy cubed minus cy squared plus cy minus c plus y squared plus 1. Okay. All right. We've done a lot. Okay, well, what do we get? Well, let's group our terms. Well, how about in the cube terms? Well, we have an a y cubed and a cy cubed. So we're going to get a plus c y cubed. All right, how about the squares? Okay, so we have a minus 2a. We have a plus b. We have a minus c. And a plus 1. Okay, how about the y's? Well, we have an a. And what else do we have? We have a minus 2b. And we have a plus c. And our constants. Okay, what do we have? Well, we have, well, everything there has a y until, oh, there's a b, and a minus c, and a plus 1. So plus b minus c plus 1. Good. Now, what do we do with all of this? Well, remember, we had this other idea which said everything has to match, the coefficients that is. So the constant 4 has to match with the b minus c plus 1. The minus 2 has to match a minus 2b plus c. And then you're like, well, wait a second, there's no y squared over there. Well, that means this has to be 0. There's no y cubed, which means this has to be 0. So, great. Now we have some equations to work with. Well, and now we start getting our hands a little bit dirty. Now, the first thing we can spot is some easy things to say. Well, look, a plus c has to be 0. Okay, let's use that. So we know that a has to be negative c. Now notice this last equation here. A plus c has to be 0. So if I know that a plus c is 0, and a minus 2b plus c equals minus 2, I say, wow, that equation tells us that minus 2b has to equal minus 2. Ah, beautiful. B has to be 1. That's good progress. Nice. Okay. Oh, look here. This is good. Now that we know B, we can come to this one. We can say, well, look, we have B minus C plus 1. And we know what B is. It's 1. So we can say, okay, so 1 minus C plus 1 has to equal 4. Okay, well, what does that tell us? Well, that tells us that C has to be minus 2, right? That's the only way that could work. And now we say, oh, A is minus C, so that says what? That says A is positive 2. And now we're good. We've got everything that we need. We've got A, B, C, and D. So we were able to, do a little bit of, hey, there's a nice guess. That gets us something. And then we say, okay, look at the coefficients. Okay, that gets us everything else. And then we're done, right? Well, we're not done yet, but we're getting closer. We're on our way. We're on our way to understanding. Okay, great. Now, of course, we can point out there were other things we could have done. We notice that we have a b minus c plus 1. And here is a b minus c plus 1. That's a 4. So we could have said minus 2a plus 4 equals 0, which would have gotten us, again, a equals 2. There's all sorts of things you can do. And I think it's kind of like a puzzle, right? We're trying to unbox everything. And if you look at it as like, a mystery to solve, it can make it a little bit more enjoyable. And we do want to enjoy our problems. So we still have to finish up. So where are we at? So let's see what we have. We have A is 2, B is 1, C is minus 2, and D is positive 1. All right, so there we go. All of our pieces nicely set up. And so we've done the hard part, which is we've done the pulling apart. When we go to write it, notice how we have y squared plus 1. So we're going to actually write that in two separate pieces. So this integral is, I'll have 2y over the y squared plus 1 plus 1 over y squared plus 1. So I'm just pulling apart using the fact that addition works nicely in the numerator. Another way to think about partial fractions is how do you handle addition in the denominator? And that's what's really happening with partial fractions. Like if you have lots of addition in the denominator, it's like, pull it apart, and life is good. Okay, so then we have minus 2 over y minus 1. And here we have a y minus 1 squared. We can even write that as y minus 1 to the minus 2, just to sort of foreshadow what's to come. So now, let's go through it term by term. How do you integrate 2y over y squared plus 1? Well, notice the derivative of y squared plus 1 is 2y. So it's like, oh, I have a function downstairs, the derivative upstairs. That's natural log. So the integral of the first piece, natural log y squared plus 1. Integral of 1 over y squared plus 1, one of our favorites, arctangent. So plus arctangent of y. Integral of 2 over y minus 1 is natural log of y minus 1. Integral of y minus 1 to the minus 2, well, that would be y minus 1 to the minus 1. Okay, so that's 1 over y minus 1. But remember, you'd have to divide by that new exponent. So we'd have to divide by minus 1, which really makes it a subtract 1 over y minus 1. And of course, plus c. And there we go. That's it. That's our answer. Wow. What a problem. What a problem. And if you can get comfortable doing this, I'm not going to say this is the hardest possible problem. We're going to do some other challenging problems. But this gives you a really good sense of what you can do. All right. Well, let's keep doing more problems. The more we do, the better we're going to get. So, our next problem. Find the integral of 1 over e to the 2y plus 2e to the y plus 1 dy. Now, is this a partial fractions problem? And the answer is no, it's not a partial fractions problem. See, there's a problem here. It's not a polynomial downstairs. And so it's sort of like, I can't really make progress here. Not yet. Well, what can we do? Well, one of the things that we can do is we can say, sometimes they write things in ways that are misleading. And we're onto their tricks. We know what they do. What am I talking about here? This e to the 2y term. There's a couple ways to think of e to the 2y. Now, one way, of course, is as e to the 2y. There's nothing wrong with that function. It's a perfectly fine function. But another way you can think of this is e to the y squared. And so if we think of it in that way, we say, oh, look at the denominator. It is kind of like a polynomial, but instead of having, like an x, it's like e to the y. Okay, this is suggesting something. Let's introduce a new variable, and we're going to call it u. So we're going to make u equal e to the y. Now, the nice thing about that is we say, okay, then we would have u squared plus 2u plus 1. Okay, so that's a good substitution to make as far as making the denominator look like a polynomial. On the other hand, of course, what would have to happen? Well, we'd have to say that du would be what? Well, it would be e to the y dy. But there is no e to the y dy. But that won't stop us. We say, okay, hey, we know what e to the y is. E to the y is u, so this is u times dy. Or, put another way, dy is 1 over u du. So, what can we do? With this substitution, we can say, all right, we have this 1 over u squared plus 2u plus 1. That's our denominator. And then a 1 over u du. All right. And now we're like, okay, this is a nice thing. It's a polynomial, 1. 1 is a polynomial over a polynomial. Good. Life is great. Now, we proceed. Certainly the numerator tells us no need for division. We do need to do one thing to our denominator before we go too much further, which is to say, this u squared plus 2u plus 1, it's really the same as u plus 1 quantity squared. Okay, so we really have the integral 1 over, and I'll write it as u times u plus 1 squared du. All right, so time for us to do our partial fractions magic. All right, what do we have? What do we have? Well, we have the following. Okay, so 1 over u times u plus 1 squared. Well, that's equal to, we use the denominator to make the form. So there's something over u, something over, now u plus 1 squared. It's a linear term, so you work your way up. U plus 1 and u plus 1 squared. Okay, so those are the right pieces downstairs. We're going to have an A, a B, and a C. It's a linear term squared. The inside part determines the form. So keep that in mind. It's when you have an irreducible quadratic that you'd have something like a cy plus d, but we don't have an irreducible quadratic. Another clue, of course, remember, is that the number of unknowns matches the degree of your original denominator. All right, well, multiply. And here, multiply by u times u plus 1 squared. And if we do that, we'll get 1 equals a times u plus 1 squared plus b times u plus 1 plus c times u. Great. Wonderful, actually. And now we're like, hey, let's choose. In fact, I like the choose method because the choose method, it feels like things come quicker because things often come quicker. All right, so what are some good choices? Well, let's choose u equal 0, right? Because I see a u and a u there. So those will go away. So I get 1 equals a times 1 squared. So 1 equals a. Aha! I can now solve for a. That tells me a equals 1. Well, okay, that one was kind of redundant, but all right. Well, how about u is minus 1, right? Because there's some u plus 1s there. So we get 1, goes away, equals minus c. Okay, c equals minus 1. Now, what about the last one? Well, you might say, well, Steve, you're out of luck. You got to expand. The thing is, I don't have to. I can just choose any other number I want. I can always pick numbers. We try to pick numbers which are nice, but we can pick numbers that aren't nice, especially if we're down to just one thing we don't know. So we pick 0, we pick negative 1, pick any other number, and make it something nice to work with. 1, right? Remember our mantra. We love ourselves. We really want to take care of ourselves. So we always try to say, let's pick things that are easy for us to work with. All right, so let's pick a positive 1. Okay, so what do we get? We get 1 equals, here it'll be 1 plus 1 squared, which is 4. 2 squared is 4, times a. We know what a is, so 4. Here we're going to get b times 1 times 2. So that is 2b. Or is it not 2b? No, it is 2b. And then we're going to get plus c. But wait, we know what c is. C is minus 1. So minus 1. All right, great. Well, now we move things around. So we can add 1, subtract 4, and we get 2b is minus 2. Or that tells us that b is minus 1. All right, great. So we know our A, B, C. So A is 1, B minus 1, and C minus 1. All right, well, now back to our regularly scheduled problem. So this integral becomes 1 over u minus 1 over u plus 1 minus 1 over u plus 1 squared, which I'll write that as minus u plus 1 to the minus 2, just in anticipation of actually carrying out the integral. Because, well, what are the integrals of the pieces? Well, integral of 1 over u, log u. Integral of 1 over u plus 1 minus log u plus 1. And then here, u plus 1 to the minus 2, well, what will happen? That'll be u plus 1 to the minus 1. And then we're going to bring the minus 1 down. It was already minus to begin with. which makes it a plus, and plus c. Now, is this our answer? No. But we did the integral part. The last thing for us to do is to say, hey, we started in terms of y. It's an indefinite integral. We have to end in terms of y. So we go through and say, well, u is e to the y. Log of e to the y. Well, that's y. Then we have log of u plus 1. So minus log of e to the y plus 1. And then we have this u plus 1 to the minus 1, which is really a 1 over u plus 1. So 1 over e to the y plus 1. And, of course, plus c. And we're done. That's it. There you go. Wow. What fun problems. What fun problems. It's wonderful that we get these answers. And they're kind of lovely answers. But it kind of also says, wow, integration is so much more interesting than differentiation. With differentiation, we learned a couple of rules, and it's like, okay, all right, we know the rules, just apply the rules. But with integration, it's like, ooh, interesting things could be happening. So, you wouldn't look at this function and say, aha, this is what it's going to be. No. You got to do something. There's some interesting things going on behind the scenes. All right, well, let's keep going. Our next problem. Find the integral 3 sine of t divided by cosine of t minus sine squared t minus 1 dt. All right, well, it feels kind of like this should be a trigonometric integral, right? It doesn't feel partial fraction-y, not yet, but we know, look, things can happen. As you work with the integral, it will transform along the way. So even though it may not look like a partial fraction yet, it could become one. So let's think about it. Now, one of the things to sort of start looking for is thinking about potential substitutions. Substitution is such a powerful method that we're like, if we can see a potential one, we should start trying to say, let's see if we can make it work. And one of the things that I like to spot when I'm looking at a problem, and I hope you get into this habit too, is to say, if I'm thinking of doing a substitution, I can say, do I see a nice derivative? In other words, is there something like, ooh, that's a derivative of a function I know. And I see this lovely sine of t sitting right there. And I say, sine of t dt, that's actually a derivative of something. It turns out, if you take derivative of cosine, you essentially get sine. Well, there's a minus involved as well. But, all right. So one thing we could think of is we could say, you could think of this as, I'll write this as 3 over cosine t minus sine squared t minus 1, and then a sine t dt. So if we were thinking of this as being our du, what we would need to do is, the question is, okay, remember we said the derivative of cosine, that's what gives us our sine, is can we write in terms of just cosine t? And if the answer is yes, then it's like, aha, great substitution ready for us. Well, the only thing that's not cosine is that sine squared. But we start thinking, oh, wait a second, sine squared, there's a really nice fact that says sine squared is a lot like cosine squared, because you have that lovely sine squared plus cosine squared equals 1. Aha, idea. Well, what's the idea? We're going to rewrite that. So this is really the integral of 3 over cosine t minus 1 minus cosine squared t minus 1 sine t dt. Great. Wonderful. Well, let's clean that up. What is that? Well, that's the integral of 3 over, well, minus minus makes a plus, so I'll put that in front, cosine squared t. Then there's a plus a cosine t, and then minus 1, minus 2. All right. Now, we're ready for our substitution. So, here we go. We're going to let u become cosine of t, and du is minus sine t dt. Well, let's just move the minus across. So minus du is sine t dt. Now, we're like, wow, cool. What do we have? Well, we really have 3 over u squared plus u minus 2 times the sine t dt is a minus du. Okay, now we're a lot more comfortable. We say, oh, okay. Well, now we know why we're doing this problem in this session, because we have a rational function over a rational function. Well, what's next? Next thing to do is to think about the denominator. Can we factor it? Yes, we can. How does it factor? Well, you might say, Steve, you're really optimistic. Well, just because I've done this one before, but also because in order to do partial fractions, you really got to be able to somehow factor, and unless it's already irreducible, but then there's no partial fractions at all. Here, what do we have? We need two things that multiply together to give minus 2, but add together to give positive 1. Well, that's not too hard to come up with. If we did u plus 2 and u minus 1, that would work. All right, good. Well, now we're going to move aside, and for a moment, we're going to jump over and do some partial fractions. So what do we need to do? Well, we need to work on this form here. So minus 3 over u plus 2 times u minus 1. Well, that's downstairs. That tells us our form. U plus 2, u minus 1. Okay, and there's something over u plus 2, something over u minus 1. So that's our form. We've now got our mold. We just have to figure out what a and b are. Clear the denominator. Clearing the denominator, we get negative 3 equals, so we're multiplying everything by u plus 2 and u minus 1, a times u minus 1 plus b times u plus 2. All right, it's a similar process we've done before. I ran out of space to put what we're multiplying by. And this looks like a good time to choose wisely. Whereas a good choice will get us closer to our answer. Let's do it. Okay, so what's some good choices for you? 1 looks pretty good. So pick u equals 1. What do we get? Negative 3. And that term goes away. And we're going to get b times 3. Okay, so negative 3 equals 3b. Well, okay, so b equals minus 1. All right, great. Good. So this here is minus 1. All right, and another good choice, minus 2 looks pretty good, right? Because that would knock that term out. So choose u equals minus 2. We're going to get minus 3. Minus 2 minus 1 is minus 3a, and that term goes away. Okay, so that says a is plus 1. Okay, so that's plus 1. All right, great, good. Well, we're almost there, right? We are, yeah, we are. Okay, so back to our integral. So what we can now say is that this integral is really, look, 1 over u plus 2 subtract 1 over u minus 1 du. All right, so easy parts to integrate. That's the natural log u plus 2 minus natural log u minus 1 plus c. And we can, even if we wanted to, we could actually combine them together. So we could say, look, that's really the natural log of u plus 2 over u minus 1 plus c. Now, the last thing to finish up is we've got to go back to where we began. We began in terms of t, so we need to finish in terms of t. And we say, well, we know what u is. U is cosine of t. So we end up with natural log of cosine of t plus 2 over cosine of t minus 1 plus c. And that's it. We're done. Wow. Cool. Fun problem. Fun problem. Now, one thing you could do, if you really wanted to, is you could say, you know, Steve, cosine of t minus 1 is always going to be less than or equal to 0. So if you put it as 1 minus cosine t, then you could really drop the absolute values. Yeah. But that's okay. This is still correct. So we're good to go. We're good to go. All right. Great. I think they were trying to sort of hide what was going on. That sine squared at the beginning, that was very much an obfuscation. But we got it. We got it. No problem. No problem. Good. All right. I think we have time for one more problem. One last one to finish it up. All right. So let's see. What do we have? Find the volume which results from rotating the region where x goes from 0 to 1 and y goes from 0 to this expression 5 minus 3x over x squared plus 1 times x plus 4. Okay, so that's actually the curve you see there. And we're going to spin it around the line x equals minus 1. All right, well, good. It's a volume problem. Okay, well, Now, when we see a volume of revolution, one of the things we have to decide is what's the right method to use. Because there's a couple of different methods that show up when we talk about volumes of revolution. And the way I like to figure things out is I like to say, well, let's just think about how we break things up. So we think about slicing. Because we have a function of x, and I don't want to try to find the inverse of this function, we really want to stick to integrating with respect to x. So when we think of spinning, we're really thinking of a slice as looking something like this. And we say, okay, what happens if we spin this slice? So when we spin that slice, what shape do we form? That will dictate our technique. And we see the shape that's being formed is like a little cylinder. It's a shell. So this is shell method. All right, great. So how does shell method work? Well, the idea is the following. The volume is found by adding up. Of course, that's how integration always works, is you add up, start to finish, and then we're going to have 2 pi, a radius, a height, and a thickness. That's the setup for the shell method. Okay, so let's talk about what the pieces are. Now, the height, that's actually just going to be how far up and down we go. So it's from this bottom curve, 0, to this top curve. So it says that this piece right here, that's our height. Our thickness, that's our dx. Our bounds are 0 and 1. And what's the radius? Okay, so that we should think about. Well, what do we have? The radius is how far we are from where we're spinning. So that would be this distance. So we're at x. How far are we from just an arbitrary x to x equals minus 1? Well, what we can do is we can do a subtraction. So we say, okay, so right minus left, high value minus low value. X minus minus 1 makes it x plus 1. All right, so there we go. That's our radius. All right, well, great, wonderful. Let's see what we can do here. All right, So we get the following. Our volume is going to be integral 0 to 1 of 2 pi times x plus 1 times 5 minus 3x over x squared plus 1 times x plus 4 dx. Okay, let's not worry about the 2 pi. That's a constant. So most of our job is going to be really saying, what can we do with this part? Now, if you look at it, what do you see? It's polynomial over polynomial, which rational function. So it's like, okay, good thing for today. Let's check our degrees. Say, do we need to worry about long division? Upstairs, we have, it's going to be a squared term because there's an x and an x. Downstairs, it'll be a cube. So we're good to go as far as long division. No need for long division here. All right, well, let's do some work. Okay, so put some space here. So what do we have? We have really x plus 1 times 5 minus 3x, and divide that by x squared plus 1 times x plus 4. Now, we have an irreducible quadratic. Okay, that's all right. We've done that before. So what are we going to end up with? Well, we're going to have something over x squared plus 1 and something over x plus 4. Now, for the irreducible quadratic, you have to have two terms when it's an irreducible quadratic. So ax plus b. For this term, just a single value, c. Okay, now we proceed, as we often do, clear your denominator. So, going to multiply everything by x squared plus 1 times x plus 4. And if we do that, what do we get? Well, we're going to get x plus 1 times 5 minus 3x equals ax plus b. And here the x squared plus 1's cancel, so times x plus 4 plus c times x squared plus 1. Okay, because the x plus 4 is canceled. Now, let's choose. And because I always like to choose first, because I feel like if I can make some easy choices to get a couple of values, then the last part is not so bad. If I just forge ahead and start expanding, it's like, okay, I don't know anything, and then I have to really start sort of reaching around in the dark trying to figure out what's going on. All right, so is there a nice choice here? Well, because of that x plus 4, there's a beautiful choice. Let's choose x equals minus 4. Okay, so let's see what would that be. Minus 4 plus 1 is minus 3. So we have a minus 3. Then we have 5 minus 3 times negative 4. Oh, well, that's actually kind of big, right? That's going to be 5 plus 12. That's 17. Uh-oh. Ugh. All right, well, keep going, right? Let's have faith that they gave us a nice problem. The first term goes away, so then we're going to have plus c, and then we're going to have minus 4, oh, sorry, not plus, equals, because we forgot to write the equals. So we're going to have 0 plus c times minus 4 squared is 16 plus 1 is 17. They were nice to us. Oh, see, the 17s cancel. And so now we say, look, we know what c is. It's negative 3. Perfect. Perfect. Woohoo. Ha-ha. Nice. Okay, so negative 3. Now you might say, well, now we're just like, but actually there is another nice one. Okay, is there any value that can knock out anything? And notice you have an a times an x. 0. 0, what a lovely number. You know, sometimes we don't like 0, but I'll tell you, it's a handy number to have when it's available. Okay, so if you plug in 0, what do you get? Well, you can get 1 times 5. So 5, that's actually makes that lovely. 0 plus b, and then times 4. So we get 4 times b, and then we get plus c. All right, but now we say, hey, we know what c is. C is negative 3, so that's really 4b minus 3. And now we're like, okay, so, what can we do? Well, that says 4b is equal to 8, which really tells us b is 2. Great, wonderful. So now we know what b is. B is 2. So the last thing is we just have to pick a value for a. We got to figure that out. And so we can group coefficients, or we can pick any number we'd like. Let's just pick a number. Now, we can pick any number. It doesn't matter. So how about 1? 1 is often a very nice number to work with. Okay, so if we plug in x equals 1, what do we have? Well, we're going to get 1 plus 1 is 2. 5 minus 3 is 2. Okay, so we'll get 2 times 2, which is 4, equals a plus b. Well, wait, we know b is 2, so that's a plus 2 times 1 plus 4, which is 5. And then we're going to get 1 squared plus 1 is 2 times c. So that'll be really minus 6, because 2c is minus 6. Or, if you like, I can say 5 times a plus 2 equals 10, because I can add 6. Okay, so then I can say, all right, a plus 2 has to equal 2, right, because I can divide by 5. Okay, so that tells us, hey, a is 0. Nice! Beautiful, beautiful. That is cool. Okay, so a is 0. Gone. Nice. All right, well, now we've done all our partial fractions. So, coming back, returning to the problem. So what do we have? We say, look, there's a 2 pi, which we always had. I'll pull it out and go 0 to 1. And this part here becomes 2 over x squared plus 1 minus 3 over x plus 4. And now we're really in good shape, because these are both lovely pieces to work with. Okay, so we have, this is 2 pi, and the first part, the integral of 2 over x squared plus 1, is 2 arctangent of x. And then the second part is natural log of x plus 4. And we're going to go from 0 to 1. All right, well, so what is that? So we have 2 pi. Now, arctangent of 1. Arctangent of 1 is pi fourths. So we have pi fourths times 2, which makes that pi halves, minus 3 natural log 5. Okay, subtract. Plug in arctangent of 0 is 0, minus 3 natural log 4. Okay, so notice that minus, minus, we can make this a plus. And so what do we end up with? Well, if we want to, we can multiply the 2 pi in, and we can say, look, that's really 2 pi times pi halves is a pi squared. Okay, 2 pi times pi halves. And then we have a natural log of 4 times 3 and a natural log 5 times 3. So the 3 times 2 pi makes us 6 pi. And then we can do a log of 4 over 5, because it's plus log 4 minus log 5. And logs, subtraction, becomes division. And we're done. That's it. That's the answer. Wow. Wow, what a fun problem. What a fun problem. Good. And, well, these are all fun problems, of course. Keep practicing. Keep practicing. It really takes a while to get used to figuring out the forms, working out how do you get the coefficients. But once you get the hang of it, it's actually a fun tool. And I hope you enjoy it. And I hope to also see you again. Have a great day.